I hope you all can see my screen clearly and hear me too. Let's start with the class. A very good morning to all of you. We will start with the class now. And then after the class, we will meet at Google Meet for our regular discussion. The link is the same which we had used earlier. Good morning, Vinod. Good morning, Tanay. I hope you all are well and working hard on your studies. Last night I shared a document with you all which had some suggested practicals. So do look at them and then suggested project works. So do look at them and then let me know in today's practical discussion. Today's practical discussion we will start at around 12:45 sharp and then we try to wind up early because staff has a meeting at 2 onward. So we will like to finish it a bit early before that. Okay. So let's start. I have a problem for you. I have selected as we had planned. We were supposed to take some of the rotation problems. We took one in the last class and maybe one or two today, which are fairly comprehensive. So I have one problem here. For those who are watching this on small screen, I will enlarge this so that you can read it carefully. A cue ball, a uniform solid sphere of mass m and radius r, is at the rest on a level pool table. So pool, pool game, billiards game, where small balls are hit by a long thin stick, which is normally called as cue. Using a pool cue, you give the ball a sharp horizontal hit of magnitude F at a height h above the center of the ball. So at a height h above the center of the ball, you give it a sharp hit. The force of the hit is much greater than the friction force that the table surface exerts on the ball. So one can see that this suggests us that when this force is present, you can ignore friction. The hit lasts for a short time interval delta t. For what value of h the ball will roll without slipping? If you hit the ball dead at the center, the ball will slide across the table for a while, but eventually it will roll without slipping. What will be the speed of its center of mass then? So let's try to address this problem. So this is my diagram any which way. So all I can do is I can use this to draw my vector diagram. So maybe I will place it here and see if I can draw my vector diagram. Now, what are the forces acting on it? So first of all, let me just draw a circle which resembles like this, and keep it transparent. Now this is going to hit at this point, so I will have a force which is working in this direction, and here it is. So this will apply a force. Let me call this force as capital F, and obviously there is a friction present here, so friction will work, as you can guess now, in the reverse direction, because the attempted motion is happening towards the right side. The friction will work towards left side. So that is an important thing to notice, because students make problems or confusion in the direction of friction. So that is, these are my two forces which will work. Along with the other force that will work is mg, which is in the downward direction. So mass of the ball is m, so mg will work in the downward direction, and normal reaction will work in the upward direction. While drawing the diagram, I take care that this forward force is much greater than the reverse force. This is R, so my R is, uh, I can simply, R and H, I can simply leave for imagination. And now technology allows me to remove my background image. Oh, everything has gone black. Fair enough. So now, or let it be there. So these are my forces working. Now I can calculate looking at the first thing. Now whenever the force this is applied, you can see that it is a force applied for a very small interval of time. So whenever you apply force for a very small interval of time, then the concept that comes into picture is impulse. So what you are doing is you are applying an impulse to the sphere. You are not only applying a, a linear impulse, but you are also applying a rotational impulse or angular impulse. So the impulse momentum theorem kicks in. Does anyone remember what is impulse momentum theorem? So the impulse momentum theorem, if you recall, says that the amount of impulse applied is equal to change in the momentum. So if the impulse is the linear impulse, the change in the momentum is the change in linear momentum will be considered. If the impulse is rotational impulse, then change in angular momentum is considered. So now let us see how do we write this. So if I have to write the linear impulse, then the force applied is F by this. So this force applied is F. So I write linear impulse F, and let us say that the force works for the amount delta t it's given. Even if it is not given, we can assume. So F is up, force is applied for the small time interval delta t. So F delta t will give me my linear impulse. This has to be equal to change in the momentum. So let us say that it acquires a velocity which is equal to v0. So its final momentum is mass into v0. So the sphere's mass is m and the velocity is, the acquired velocity is v0. Why am I writing 0? Because I'm still assuming that when the motion begins at time t is equal to 0 and the velocity obtained is v0. Now, before the motion has begun or before the impulse has been applied, what is the momentum? So the sphere is at rest, and since it is at rest, its initial momentum is 0. So impulse momentum says that impulse applied, which is the left hand side, has to be equal to change in momentum. So this is the momentum after the hitting. Momentum before hitting is 0, so we need not write it here. So this is impulse momentum theorem applied for the linear aspect of this interaction. But remember, there is an impulse momentum theorem which will work here because this will try to induce some rotation. Since it tries to induce some rotation, the impulse momentum theorem for rotational component also will get into picture. So what could be the impulse momentum theorem for rotational aspect? What is rotational impulse? So remember, rotation, just like this impulse is F delta t, rotational impulse is torque tau into delta t, and that is equal to I omega, that is the angular momentum. So you can see that this is in parallel with this. Now how do you calculate your torque? Now the force is applied. To calculate torque, you need a point about which you can calculate the torque. So in our frame of reference, we will take center as the origin and we will calculate all the torques about the origin. So if origin is 0, the line of action of this force is this, and this separation is h. So lever arm is h, the line of action of force is F, so the torque is F into h. So I can write F h delta t, and that is equal to I omega. Now, having said that, when you so for what we have done, so what actually we are doing is we are finding out, or we are uh, deducing that after the hit has taken place, after the ball has been hit, the ball will acquire a linear velocity which is v0 f delta t upon m, and it will acquire an angular velocity. I may call this angular velocity as omega 0. So it will acquire an angular velocity as well. So these are the two things. No, it is, well, it can be. You can calculate. All I'm trying to say is, Vinod, if you calculate the torque about the lowest point, see, the point about which the torque one should calculate, ideal choice is one, ideal choice of the point is one about which the torque due to most of the forces will reduce to 0. So if you take center point, then torque due to normal reaction is 0, torque due to mg is 0. Only torque that will work is torque due to friction, and when it is hit, torque due to F. If you take the lower point, then only torque due to friction will be 0. Torque due to this, three forces, torque, three torques will come into picture. Friction will be everywhere. Friction you have to calculate. Not in this equation, because as I said, yes, I mean that's a good point, Vinod. As I said, you look at this, the the horizon, the problem says that the force of the hit is much greater than the friction force. Since the force of the hit is much greater than the friction force, when it is being hit, I can ignore friction because the torque due to friction is negligible compared to torque due to this force. Well, I'm not getting those last two lines, so maybe we can post lecture discussions. We can talk about more on this, Vinod. So let me go ahead. Right now, I'm calculating, just reminding you all, I'm calculating all my talks about the center point. Let me finish this, and then if you still have doubts, then we can discuss, or we can discuss post lecture. So let's go ahead. So this is my torque and this is my linear momentum. I may call this as equation 1 and I may call this as equation 2. Now what is the question asks you to derive it for the rolling without slipping. So what we want is to figure out the condition under which the rolling without slipping happens. So now we know that what happens here is the center of mass acquires a linear speed v0, and that linear speed v0 can be determined from equation 1, and it also the ball acquires, or the sphere acquires, an angular speed omega 0, and that omega 0 can be given by this equation. Now if it's happening rolling without slipping, then the center of mass and the periphery, any point on the periphery of the sphere, must have the same velocity. But any point which is on the periphery of the sphere satisfies the formula, that circular motion formula, V is equal to R omega. So, or R omega naught in this case, any point which is on periphery, and if it is slipping, if it is rolling without slipping, then any point on the periphery must have the same linear velocity as that of the center of mass. Therefore, V0 is equal to V plus R omega 0. So this is the defining condition. Now I can put the value. So you can see V0 is nothing but F delta T by M. So I will simply write it here. I'm just squeezing a little bit. F delta T by M. This is my V0 is equal to, I will put R here. So let R be there as it is. My omega 0 is Fh delta T, Fh delta T divided by my I value. So you can see a lot of things will cancel. F delta T and F delta T will cancel. So you have M here in the denominator. I am interested in finding out H. So H gives me, this formula gives me H as, now look at it carefully, I will go up, R will go down. So it will be I divided by MR. Now depending on what kind of body you have, you can put an I. For example, if in this case it is a solid sphere, so I is 2 by 5 mr square. So if you put 2 by 5 mr square, what h will you get? Think about it. So 2 by 5 denominator, there is nothing. So it's 2 by 5 mr square. So m will cancel, 1 r will cancel. So your answer is 2 by 5 r. Now look at it further. What happens if it is a ring and you want to hit, suppose, or a hollow cylinder, so that you want to hit. So for a hollow cylinder, you know it is mr square. So if it's a hollow cylinder, then h will become, you put mr square and it will become r. Now when h becomes r, I mean this is for a solid sphere, and this is for a hollow cylinder. So h becomes r means, remember, I'm looking at a height, h starts from the center and goes above. So if h is equal to r means if it's a hollow cylinder, I have to really hit at the top, because I have to hit at a distance r from the center. So that actually solves the A part. If you hit the ball dead on the center, so let's do the B part now. What happens if you hit the ball dead on the center? So if you hit the ball dead on the center, the ball will slide. It will start sliding. You are hitting at the center. So this first equation would still be valid. F delta t is mv0. So it will acquire a linear velocity. But if you hit it at the center, then this equation will change, because if you are hitting at the center, then h is 0. This term is 0, and you are not applying any torque by the q, and therefore there is no rotational impulse to the system. So omega 0, or initial angular velocity, is 0. So for B part, if you hit at the center, V0 I know, V0 would be given by, as we have already discussed, F delta t by m. But your omega 0 is 0. So it will start with a linear velocity. If you have a large force, then it will start with a huge linear velocity, while it will not have any angular velocity. Vinod, as I said, when this force is working, during the contact time delta t, when capital F is working, when the Q is in contact with the ball, we can ignore friction, because the problem warrants us to do that. It clearly tells that the force of hit is much greater than frictional force. So when the Q is in contact, in that time period, I am ignoring friction. Friction is not much. Yes, when Q is not in contact, then friction will play a role, because then in that case, in the horizontal direction, that is the only force which is working. So again, reminding you all that remember, this is a very, as I said, this is a comprehensive dynamic problem. In the first case, Q is in contact. When the Q is in contact, Q force is very strong as compared to friction. So we can ignore friction. But when the Q leaves, when the ball moves ahead, then your friction is the only force. So that has to be considered. We cannot ignore it. So I'm coming to it. So to begin with, when the Q hits, it acquires a linear velocity. it does not acquire an rotational velocity or angular velocity if the Q hits along the center line. Okay, so as a result, the ball tends to slide. Remember, you are hitting at the center of mass. Anything you hit at the center of mass, the ball tends to slide. So ball will tend to slide. As the ball tends to slide, the friction will work backward. As the friction works backward, it will do two things. Number one, it will apply a linear acceleration in the backward direction, and it will induce a rotation in the clockwise direction in my diagram. So friction will apply a torque this way, as I have shown it here. So the friction will induce a torque which will actually induce angular velocity. So, and it will apply an acceleration in its own direction, which is a deceleration because the velocity is in this direction. So what friction will do now, once the Q contact is lost, the friction takes over. Friction brings in two things. Friction applies a torque, so it increases angular velocity. Angular velocity will go on increasing, and it applies a deceleration or an acceleration opposite to initial velocity imparted by the Q. So the velocity will go on decreasing. So these are the two things that friction will do. So let's take that into account. So what is happening now is friction will apply. So I can write Newton's law along x-axis. F is equal to ma. Remember, this is my frictional force, so it has to be equal to mu times normal reaction. But normal reaction, this is a horizontal surface, so it is mg. Of course, my mu has to be there. I'll write it at the end. Now, I can cancel out small m, so friction force will not depend on m, and the acceleration induced by the friction force is mu times g. Okay, now going ahead, this will impact the velocity. So velocity at any time t is nothing but velocity at time 0 minus at. Remember, it's a deceleration. The velocity is towards right, friction is towards left, so acceleration is towards left. So now I can put the values. The values I can put here is, let me leave it as V0 to begin with. So this is my V0, because answer asked is in terms of original velocity. If you hit the ball dead at the center, the ball will slide across the table for a while, but eventually it will stop. What was the speed of its center of mass then? So you have to find out V, and it is in terms, you have to find out in terms of V0 only. So V0 is, let it leave it as V0 minus, your A is mu G, so I can write it as mu G T. So this is my equation. Now let's bring the torque. Force of friction applies a torque. Torque applied by the friction about the center. Again, I'm measuring about the center is equal to torque is friction into R. So I will write F into R, and that will induce rotation, so it is equal to I alpha. So this will be my friction. That will give me alpha as a value which is equal to, what would it give me? Let's have a look. It will be F R divided by I. I can put f as mu mg, that I will do in the next step. Now this alpha is in the clockwise direction, and it will introduce angular acceleration, because of which the angular velocity will rise. So now I can write the angular velocity. So the angular velocity omega, well, let me put all these things at some place. Let me see if I can pull it on the next page. I think I can. So I'll leave it here just for the reference, and later we may not need it. So yeah, so now your omega is increasing here, so I can write omega at any time t, a kinematical equation. Remember, initial omega is 0, so 0, this will increasing, the torque due to friction will increase omega, so it will be alpha t. So your omega at any time can be written as alpha, which is f r by I into t. But f is nothing but mu times mg r divided by I into t. This is my omega. So omega is equal to, now I've got omega as a function of time. I have got velocity as a function of time here, if you can notice. So this is my velocity as a function of time. This is my omega as a function of time. Now just try to visualize. As the time progresses, V0 will decrease because your A is in opposite direction. As the time progresses, omega 0 will increase because this is working in the clockwise direction. So a situation will come. So initially it is more of slipping and less of rotation. But a situation will come when the condition for perfect rotation will be matched, and at that time perfect rolling will begin. So perfect rolling condition is, as we all know, V is equal to R omega. So I can use this. V is already known, V0 minus mu gt. So this is V0 minus mu gt is equal to R. R value remain as it is. Omega is here. So I can write mu m g and then multiply by R. So it will become R square divided by I into t. So this condition has to be satisfied when both the bodies will meet. So V0 is equal to, I can mu g plus mu g can be taken common. So this will become 1 plus, this goes this side, mu g is common. So 1 t I will take common. 1 plus mr square divided by I into t. So the time at which both will become same is V0 in the numerator and in denominator we get all these stuff. So I leave that for you people to finish now. You put the value of I for a sphere is 2 by 5 mr square. So you can put it in this case and then solve it a bit, and you will get your answer in terms of V0, the time after which it will get into perfect rotation. Once the time is known, then I can go ahead and calculate the distance as well. Sometimes they ask what is the distance at which it will get into perfect rotation. So you can use this to find that as well. So this is how this problem will go. We have some time. So maybe I will introduce one more problem of rolling where I can give you the parameters and perhaps you can solve it further. So you have a ball. A bowling ball rolls without slipping down a ramp which is inclined to an angle to the horizontal. So this is now a ball which is inclined right now. What are the ball's acceleration and magnitude of the friction force on the ball? Treat the ball as uniform solid sphere, ignoring the finger holes. Ignore all these things, this imperfection. So I can draw a diagram which can be diagram can be drawn very quickly. You have a ramp. The ramp has some angle. In the diagram, the angle is beta. You have been given a ball, so I can draw a little circle. Maybe I can fill it with some color. This is the ball. Now what are the forces acting? Let me make it slightly bigger so that I can show the forces little more clearly. Yes. So what are the forces working? So basically you are familiar here that things will slightly change because of the tilt. So it will tend to slide down. Remember, if the surface had the surface been very smooth, it's a very smooth surface, then it will not roll, it will slide. Why will it slide? Because your mg sine theta, as you are all familiar, your mg sine theta works in this direction. Mg in this case, it is sine beta. Okay, mg sine beta works in this direction. Remember that normal reaction will work here. So this is my normal reaction. My mg, as you are all familiar with these, so I don't have to put much detail. Mg cos beta, I should have used for writing white only and yellow. Mg cos beta works this way. Friction, where is friction working? The friction is working in this direction. This is the direction of friction. Remember, it's the friction which brings a rotating torque to the system, and because of that the rotation comes in, and because of that the ball starts rolling down. Had there been no friction, the ball would just been slipping because of mg sine theta. So this is how the situation comes. Acceleration is in this direction. This is the direction of acceleration. The rolling is happening this way. So this is the direction of alpha and omega, both. So this is my situational diagram. I can remove this part. Now these are my forces. Now I can give you the initial conditions to solve the problem, and then we can stop, go to the meat and discuss a few points important. So remember that both Newton's law for rotational motion and Newton's law for linear motion, both will apply. So if I have to write it for linear motion, I will write sigma F is equal to ma. So sigma F is nothing but mg sine theta in the direction of A, which I take positive direction, and this as negative. So I will write mg sine beta minus friction is equal to ma. So this is my one equation. Now along, I know that total torque. Now what is the torque? Now I will calculate again torque about the center. So total torque about the center due to normal reaction 0, due to mg cos beta 0, due to mg sin beta 0. So only force that is applying torque about the center is F, which is R times F. So I will write it as R F as my torque, and that has to be written as I alpha. So this is my second equation. My friction is, as you all know, is mu times normal reaction. But what is normal reaction? Normal reaction, you all know, is mg cos beta. So the friction becomes mu times mg cos beta. So this is my frictional force. And what is the condition for rolling? If it is perfectly rolling, it's a rolling without slipping. So it's a perfect rolling. So if it's a perfect rolling, we all know that V is equal to R omega. If you take a derivative on both sides, then you know that A is equal to R alpha. So suggestion is you can solve this equation, put values in this equation for friction, and then link the two equations. Remember, A is here, alpha is here, so remove alpha and write A by R. So write A by R, then remove A from these two and join the two equations, solve them as simultaneous equations, and you are done with this. So that's a very important, these two categories of problems for rolling are very important. So we just covered them. Rest of the rolling problems I recommend you to practice from the reference book. So we can stop here. We will continue with our post lecture discussion on Google Meet. Thank you.